We are going to look at quantum mechanics, a question you find from a textbook or any exam or a homework or whatever. It's quantum mechanics. So there is a question. Find a wave function psi of x 0 time for a Gaussian wave function. The Gaussian wave function in the momentum space. The momentum space, so is in the momentum space, phi of k is equals to a e to the power negative a squared k minus k naught squared over 4, where a is the normalization factor. So we have to normalize that to be found. Now calculate the probability of finding the particle in this region. So step number 1, what am I going to do? Step number 1, I'm supposed to find psi of x 0. That is what I'm going to do first. Step number 2 is to find a, the normalized factor. From there, I will find the probability density function. The probability density function. Density function, which is psi of x squared. Then from there, I can find the probability of the particle in the space in that region there. For the momentum wave function, so for momentum wave function phi of k was given as, I want to use small letter k, was given as phi of k is equals to, it was given as a e to the power negative a squared of what? Of k minus k naught squared over 4. This was the momentum wave. For us to get the wave function, we use Fourier transformation. Fourier transformation, it changes the wave function of the momentum wave function into a psi wave function. So it is transforming. So how do we write the Fourier transformation? So the Fourier transformation is psi of x is equals to 1 over the square root of 2 pi, the integral from negative infinity to infinity of phi of k e to the power, I'm obsessed with negative, I kx dk. So this is the transformation we are going to use. So with the transformation, what are we supposed? Let's substitute. So substitute our momentum wave function psi k. And what do we have? We have got now the psi of x, that's a phi, and this is a psi, is 1 over root 2 pi, the square root, negative infinity to infinity, a e negative a squared of k minus k naught squared all over 4 e to the power I k x d k. So that is the substitution. Now we can do the simplest thing. Let's take the constant out of the integral. Psi of x is equals to, now it's a over the square root of 2 pi, the integral from negative infinity to infinity of e negative a squared of k minus k naught squared all over 4 e I kx d dk. That's what we... Now from here, we can reduce. We can reduce the expression by let the k prime, let's introduce k prime, is equals to k minus k naught. You'll discover that also k will be equals to a k prime plus a k naught. Now if I differentiate dk over dk prime, I get a 1. So dk is equals to a dk prime. So this is important, and this is important, and this is important. Why is it important? Because we want to substitute. So let's write our expression first in terms of k prime, in terms of k prime. So psi of x is equals to a over root 2 pi, the integral from negative infinity to infinity of e to the power negative a squared of k prime squared over 4 e to the power I. Now k is equals to this one here. This one goes in here, right? And this one goes in there. So k is equals to a k prime plus k naught or x d now k prime. This is goes to there. You see, the thing that goes here, it's coming there. So basically, what are we doing? So basically, we have substitute, simple substitution. From there, let's use the law of indices. I'm trying to show every detail so that people don't say quantum mechanics is difficult. It's not difficult. Is this a over root 2 pi, the integral from negative infinity to infinity of what? E a squared of k prime squared over 4 e I k prime x dot e I k x d k prime. Now let's take out constants that are not involved. If you look at k prime, this one doesn't have a k prime. This one has a k prime. This one has a k prime. So this has to join the outside world. So if it is supposed to join, we are going to write it as psi of x is equals to a over root 2 pi. We take out that e I k x, the integral from negative infinity to infinity e negative a squared k prime squared all over 4 e I k x d k prime. Now let's use the standard Gaussian transformation. Use the standard Gaussian transformation. Why? Because we need to solve the integration. So standard Gaussian transformation says integral from negative infinity to infinity of e I b squared y squared E I K Y dy is equals to the root pi, square root of pi, over b e of I k squared all over 4b squared. So this is the standard Gaussian transformation, and we have to use it to compare. We have to compare z. In comparison, we can see that this part here is compared to that part here. So if I take this comparison here, what am I going to get? I'm going to say that my y is equivalent to a k prime is compared to. All right. Then we can also see that my negative b squared is compared to this part here. Okay, it's this part here. You will see when I write it down. So basically I'm saying y is compared to k prime. Then I'm saying b squared is compared to a squared over 4, which means your b is equals to a over 2. Now, so what will definitely remain is, in other words, your k prime, is it k prime or it's k? It's k. So your k from the other side is actually compared to x, like this. So you have done the comparison now. So basically, what we are going to have is the square root from negative infinity to infinity of e, negative a squared k prime squared over 4 e I k prime x d k prime is equivalent to the square root of pi all over a over 2 e minus x squared over 4 of a squared over 4, like this. That will shrink down to the root of pi all over a e to the power negative x squared over a square. So coming back to our psi of we are going to put our psi. So psi of x, remember it was a over root 2 pi e to the power I k naught x, the integral from negative infinity to infinity e to the power negative a squared of k prime squared over 4 e to the power I k x k prime d k prime. And we have solved this part here. So this part, we are going to put this answer there. This answer, we can now show let's show it so differently from the other world with another color. This part here is the one we are going to put in there. So definitely what we are going to have is psi of x is going to be a over root 2 pi of e I k naught x bracket. Then we can put our 2 root pi over a e I negative squared over a squared, like this. So at the end of the day, your wave function psi will be reduced to, because you can see the maths, it's very easy now, square root of 2a over a e to the power negative x squared over a squared e to the power I k naught x. So the wave function is like this now. This is the wave function. So when we get the wave function, remember that we have to find this normalized factor here, normalization factor. But we can calculate the probability density of the wave function. We calculate the probability density. Probability density is psi of x squared, which is given as, from the theory, it's psi of x multiplied by psi conjugate of x, like this. So what do we have? We have got our square root of 2a over small letter a e to the power negative x squared over a squared multiplied by e to the power negative I k x k naught x. Okay, it's also multiplying the square root of 2a over a e to the power negative x squared over a squared dot e positive I k naught x, right? The conjugate, you can actually see the conjugate, it only affects the i's. If you look at it, it affects the I. One is positive, one is negative. So that is the conjugate. So I want to take a pathway to work like a young person, not to be like very intelligent. The pathway I'll take is very, very, for those who don't like this pathway, you can jump on the video. You can fast forward it. But this is the pathway I want to take because I want to enjoy the maths, though it's useless. So it's going to be, let's take numbers on their own, the square root of 2 and a over a multiplied by itself, square root of 2 of a over a. Then collect like terms, e negative like this over a squared dot again, collect the like terms, e negative x squared over a squared like this, and another like term, e negative I k naught x dot e of I k naught x like this. This is more like working like a primary school kid, which is so we will definitely write this as, you can see square root of that and square root of that, it's a 2, and it's a squared over a squared. E, then this one, definitely they are identical, so we will definitely have a 2x squared over a squared. And this one is more like it's gonna give you e to the power 0. And yes, e to the power 0, it's gonna be, so it's gonna be e to the power of, we can take the k naught outside, e to the power 0 like this, which is gonna give you a 1. So at the end of the day, you're going to have 2a squared over a squared e to the power negative 2x squared over a squared. Remember, this is the probability density function. There it is here, the probability density function. So this is a Gaussian function. So this is a Gaussian function, centered at 0. So we can say at x equals to 0 with an expression which we can, or a form, with a form like c e to the power negative x squared over 2 sigma x is a sigma, yes, sigma squared. It has that in that format there. So in this case we compare the exponents. So compare it. So how do we compare it? If you look very careful, 2a squared over a squared e negative 2x squared over a squared. Now if we are going to compare with c e negative x squared over 2 sigma squared, we are going to find out that our in this side we are going to have x squared all over 2x squared all over a squared compared to x squared over 2 sigma squared. That is, so in the comparison we can solve it for sigma x, okay, because it's x values. Now we will say definitely you can see that this will cancel and this will become a 4 and this will go up. So sigma squared of x will be equals to a squared over 4. That will be the sigma comparison there, which will, so the standard deviation is the sigma, which is an uncertainty. In other words, we are saying the standard deviation, which is the uncertainty position, delta x, is the sigma x there. So therefore my delta x is going to be the square root of this sigma squared. That is to say, is equals to the square root of a squared over 4 to give me an a over 2. It will give me a over 2, the uncertainty. For normalized condition, for normalization condition, we say the wave equation psi is actually, we integrate it from negative infinity to infinity. I wanted to say is the probability density square dx is equals to 1. This is a condition for normalization. So this is a condition to normalize it. So you should have that condition to normalize it. Since we have the sigma, the density with the probability density function, we can say from negative infinity to infinity of 2a squared of over a squared e to the power and negative 2x squared over a squared dx is equals to 1. So we are supposed to solve. In this case, we use again, so use the standard Gaussian Gaussian integral. Now, what does it say? It says the integration from negative infinity to infinity e to the power negative b squared x dx is equal to the square root of pi over b, this one here. So in this case, we compare. You would find that your b is equals to a 2 over a squared. So in other words, we are going to say 2 and the a modulus of a squared over a squared, small letter a, is square root of pi all over 2 over a squared is equals to a 1, right? So everything now is going to be mathematics. It's not going to be a problem. 2, the modulus of a squared over a square, the square root of a square pi all over a 2 here is equivalent to a 1. So therefore, the a squared will be equals to a over the square root of 2 pi in a symbol notation. So why we use the modulus? Because we want to choose the normalized factor, constant a, should be a real number and positive. So in other words, your a is going to be, the fourth root. Okay, the fourth root of a over 2 pi, right? Like this. That will be your. So this will be the constant of normalization when you normalize your wave function. Now, to calculate the probability p, for the probability, let's use p. Is given as probability p is equals to the integration from negative a over 2 to a over 2 of the probability of the probability distribution density x of the wave function dx there from the normalized vector. So from the normalized vector, what was our wave function? So we are saying the probability density with a normalized vector is going to be a 2 a squared over, remember, a squared e to the power negative 2 x squared over a square. Remember this part here. Then if you can remember, and it's quite okay, because remember that our a square was actually a over root 2 pi. So there is no need to write the fourth root of that. So we can write our probability density function square is equals to a 2 over a square a over the square root of 2 pi, and it's e to the power negative 2x squared over a square. That will crash down to a 2 over a square root of 2 pi e to the power negative 2x squared over a square. That will crash down to. In mathematics, if I want to deal with this too, I can call it, like, for example, if you look very careful, a 2 over a root 2 pi. I can put this 2 into a square root of 4 over a root 2 pi. I can do further like this. It's going to be a 1 over the square root of 2 pi over 4, like this. I can write it like this. You see, if I want to deal with that. Also, I can put this a in a square root so that everything becomes in a square root. It becomes 1 over the square root of a squared over a 2, like this. Or a pi, I forgot the pi, sorry, pi, like this. So that's what you're going to see next. So what am I saying? I'm actually saying that the probability density function square is equals to 1 over pi a squared over 2 e to the power this. And I said this part, if you look very careful, is similar to that because my video just cut. So I discovered that it cut. So I had written things down. Sorry for that. So it goes to here. And why am I saying this? Because the probability, we want to use the Gaussian probability distribution function density, which is similar to that. I was now writing this negative of x minus mu squared over 2a squared. Sorry for my video. So where you would find that the Gaussian is centered, so it's centered at mu is equals to 0 and sigma squared is equals to a squared over 4. So the probability density function squared is going to be 1 over the square root of 2 pi. Now your sigma square, it's actually a squared over 4, or square root, e to the power negative x squared all over 2 bracket a squared over 4, like this, which will crash down to become 1 over the square root of pi a squared over 2 e to the power negative 2x squared over a squared. Therefore, the probability integral, so probability integral is P is equals to the integral from negative a over 2 to a over 2, 1 over the square root of 2 pi sigma x squared e to the power negative x squared all over 2 sigma x squared dx. Now where we can say now let the sigma x is actually a over 2. Now to solve this, we stabilize the integration by substituting. So let's substitute z to be equals to x over sigma x. That will lead you to x. Remember, sigma is actually a over, so that will lead you to a over 2, that is equals to a 2x over a, where now our x is equals to negative a over 2 and our z is equals to 2 of negative a over 2 or over a. That will give you a negative 1. So when we say x is equals to a over 2 and our z equals to 2 of a over 2 over a is equals to 1, also we consider our dx is equals to sigma x dz. And then that will be our a over 2 dz. If you follow this, you won't have a... So therefore, we are definitely saying the probability is from -1 to 1 of 1 over the square root of 2 pi sigma x squared e to the power negative of sigma x z squared all over 2 sigma x squared sigma x dz. Now it looks a little bit complicated, but if you follow, you won't have a problem. So this will definitely boils down to a -1 to 1 all over a square root of 2 pi e negative z square over 2 dz. Right, if you follow that. Right, we have got what we call the error function. The error function is similar to the integral that we are going to deal with. So error function is actually the Gaussian function also. So it's written as error function of z. It's given as 2 over square root of pi, the integral from 0 to z e to the power negative t squared dt. So we will use the standard normal cumulative distribution function, standard normal cumulative distribution function. What does it say? Which is phi of z. So phi of z is actually 1 over the 2 pi from negative infinity to infinity e to the power negative t squared over 2 dt. So this is the normal cumulative distribution function. So since our probability distribution function is symmetric, so if it's symmetric, we will say the phi of -1 is equals to 1 minus phi of 1. So the P probability distribution function is actually the phi of 1 minus 1 minus phi of 1, which will lead to 2 of phi of 1 minus 1. So this will lead to probability is equals to 2 times 1 over the square root of 2 pi, the integral of 0 to 1 of e to the power negative z squared over 2 dz. And this is well known in the probability statistics. It's a well-known constant in statistics in probability. 1 standard deviation, so which is your mu equals to 0 region, and the probability will run to approximately 0.6827. So this will be the probability, which is approximately 68.3%. Right? That is the answer. So this, I know this might be a little bit complicated for those who want to understand, but take your time and go step by step and comment, and please subscribe. More quantum mechanics come every time. So yeah, subscribe to this channel. Thank you.